Okay, well, I'm really happy to be here. I just want to thank the organizers for inviting me. This is the second in-person conference that I've attended in the last 2 years, so this is really exciting. And I think I'm mostly over the jet lag, although probably not. So today I'm going to talk about something that's very boring compared to what we've heard about, right? We've heard about all these exciting materials, right? Altermagnets, non-collinear antiferromagnets. So I'm going to go back to boring old ferromagnets, but I'm going to talk about maybe torques which are, let's say, unconventional in these ferromagnets. And so the boring materials are still giving us some surprises. All right, so before that, I just want to quickly introduce the Spintronics theory group at IUPUI. So if you know of any graduate students who are interested in doing their PhD or potentially a postdoc who's looking for a position, please email me. All right, so here's the roadmap for today's talk. I'm going to give an introduction to the ever-growing list of spin-orbit torque mechanisms. Then I'm going to talk about spin currents in single-layer ferromagnets. And then finally, I'm going to look at novel spin torques in ferromagnetic trilayers. All right, so what is spin-orbit torque? So in a nutshell, spin-orbit torque is really receiving angular momentum from the atomic lattice. So what do I mean by this, right? So we've got some sort of magnetic heterostructure. We run a current in plane, and due to various effects that involve spin-orbit coupling, we end up getting a torque on the magnetic layer. So this happens in a lot of different ways. But what is the underlying physics that's involved here? So if we think about, for instance, spin transfer torque, this is really a transfer of angular momentum between two reservoirs of angular momentum. So the first would be carrier spins from an incoming spin-polarized current, and that would be transferred then via the exchange interaction to the magnetic order. So that's how a typical spin transfer torque would work. So the power of spin-orbit torque is that by introducing spin-orbit coupling, we couple the carrier spins to their orbital moments, but their orbital moments are coupled to the atomic lattice via the Coulomb potential. So through this extended coupling, we can actually steal angular momentum from the atomic lattice and transfer it to the magnetic order. So that's the underlying physics behind spin-orbit torque. So over here in this animation, you can see a non-magnetic material with some appreciable spin Hall effect. And so the idea is that we have an in-plane current, and the spins then split due to the spin Hall effect. They go into the ferromagnetic region, and they exert a spin transfer torque. So this is one example of how a spin-orbit torque can happen, which many of you are very familiar with. All right, but spin-orbit coupling can be good, and it can be bad, right? So for all my nerds in the audience, we have a light and a dark side to spin-orbit coupling, right? So the light side is that we can control magnetic order through spin currents and spin torques. If we think about the direction of angular momentum flow, this is from the crystals to the electronic spin, right? So here we're really stealing from this infinite reservoir of angular momentum and controlling magnetic order. But we have a dark side as well, because we can have parasitic effects such as spin relaxation or spin memory loss. And this really is just the reverse mechanism, right? We have some sort of spin polarized current or spin current or flux that's then going back to the crystal, right? So we sort of want more light side and not as much dark side. Okay, so if we look at, and this is supposed to say traditional, if we look at the traditional spin-orbit torques, we sort of have these two mechanisms which are commonly discussed. The first is the spin Hall torque, and the idea is that we run this current through the non-magnetic layer, we get a spin Hall effect, then exerts a spin transfer torque on the ferromagnetic layer, right? And this mostly damps the magnetization towards a special direction determined by symmetry, which is in plane. We also have a Rashba-Edelstein torque, which spin polarizes electrons at the interface, which then exerts a field-like or precessional torque about that high symmetry direction on the magnetic layer. But the open question really was, what is the rest of the device doing? Are these really the only torques that exist? So I got involved in this, specifically trying to ask the question, all right, let's just do this. Whether or not the rest of the device was light side or dark side, so to speak, right? So do we actually have spin-orbit coupling in the rest of the device mostly acting as something that's parasitic, or does this actually add to the mechanisms which create spin-orbit torque? And so one of the main results that we found is that there are parasitic mechanisms that happen at the interface due to an effect called spin memory loss, but we also have a generative mechanism. So via spin orbit scattering at the interface can actually create spin currents. So this is sort of like a spin Hall effect, right? But it's happening at the interface. But due to the broken symmetries at the interface, we get currents we wouldn't expect from the ordinary spin Hall effect, right? And so via these interface-generated spin currents, we can then get torques on the magnetic layer. However, as I said, the list keeps growing. So what we've also realized is that because we have an orbital Hall effect in the non-magnetic layer, we can generate an orbital current that can then flow into the ferromagnetic layer and via spin-orbit coupling be converted into a spin accumulation that then exerts a torque, right? So we can also have orbital Hall effects, which are adding to our torques. And finally, we can have torques from the ferromagnetic layer itself. So we've been hearing a lot about spin current generation in magnetic materials. One of those spin current generation mechanisms has been referred to as the magnetic spin Hall effect. So many different ways in which ferromagnets can generate a spin current. And due to symmetry arguments, they're not allowed to exert a torque in the bulk of the material. But once they flow to the layer boundaries where inversion symmetry is broken, they can exert a torque. That means ferromagnets can exert a torque on themselves if there is some overall symmetry that's broken in the out-of-plane direction. So really, we have torques which can come from every part of the device, right, that ultimately get exerted near the interface. OK, so with that, I want to take a deeper dive into the torques that specifically occur in ferromagnetic layers. All right, so why do we expect these sorts of torques to exist? So if we look at systems with more symmetry, such as a non-magnet, more symmetry means we have more constrained effects. So for spin currents, that's a more constrained spin current. But as we go to systems with less symmetry, we're going to get a less constrained spin current. So what that means is that in a non-magnet, if we apply an electric field in bulk, we're always going to get this sort of orientation where we have flow and spins which are mutually orthogonal to each other, right? So this is the spin Hall effect. It's really the only thing that's allowed by symmetry in non-magnetic materials. But if we look at a collinear antiferromagnet or a ferromagnet, where the magnetic order parameter is at some oblique angle relative to the crystal axes, we're really allowed a full spin current tensor. So that means that if we apply an electric field and we're just looking, let's say, at transversely flowing spin currents, we get everything imaginable. So it's still useful to point the magnetic order along a high symmetry direction, right? In which case we can find some differences between these. So with a collinear antiferromagnet, because we have a vanishing net magnetic order, we expect something like the spin Hall effect, but there still is a difference, right, between a flow along the nail order axis and a flow that's perpendicular. So to some extent, we can get a type of anisotropic spin Hall effect, if you want to call it that. In the ferromagnet, more symmetries are broken, and so we get currents that look like the spin Hall effect, but we get currents that are also aligned with the electric field or with the magnetization, depending on which direction you're looking at. The important point here is that the spin direction of these spin currents are not aligned with the magnetic order. That means that they can exert a torque. OK, so those are symmetry arguments, right, which result in various spin currents. But what are the different mechanisms that can actually cause these spin currents? So we have loosely extrinsic and intrinsic mechanisms, right? So not everybody agrees on the definitions of these things. So I'm just going to give you a very simple definition and try to be consistent with that. So in equilibrium, if we think about calculating a spin current as the sum of all the electronic states times the contribution from that electronic state, then after we apply an electric field, right, to linear order, we perturb this into two contributions, right? One that's going to result from the change in the electronic occupation, and another that's going to exert from a perturbation from the Hamiltonian that actually changes the spin current that's carried by that state, right? And so this is what I mean, at least in this talk, by intrinsic or extrinsic contributions, right? So typically, extrinsic contributions are going to arise from impurity scattering, whereas intrinsic contributions, you could argue, is a modification of the wave function, which is related to the Berry's phase. All right, so in particular, what I'm going to look at with intrinsic contributions are those that arise from calculating the Kubo formula. So these are the very standard Berry's phase contributions that we're all aware of. Whereas with extrinsic contributions, I'm not going to look at the typical things we look at with the spin Hall effect, like skew scattering or side jump. Instead, we're going to look at something which is a bit simpler, and I'll talk about that in a second. OK, so what sort of extra or intrinsic spin currents can we have in single ferromagnetic layers? And when can they exert a torque on that layer? right? So in this case, we have an electric field. We're just going to look at the spin current, which is flowing perpendicularly to the electric field, but we're going to vary the magnetization direction and look at all components of the spin current, right? So when we do this using density functional theory plus the Kubo formula, we get magnetization dependence that looks something like this. So in principle, at any oblique angle, you can have any spin current. But the nice thing about this is that when you actually fit these results, you get a fairly simple magnetization dependence, right? So you get a term which seems to be independent of the magnetization, and a term that looks like it has the same magnetization dependence as the anomalous Hall effect, but it's polarized along the direction of the magnetization. So for that reason, we're calling this the spin Hall contribution and the spin anomalous Hall contribution. The important thing to understand about this, though, is that if we look at the spin anomalous Hall contribution, we actually calculate its strength, right? The spin current that we get in some cases is actually greater than the polarization of the ferromagnet times the anomalous Hall contribution. So that means while this looks like a spin-polarized version of the anomalous Hall current, it's actually something that can have a effective polarization that's greater than 1. This means that this doesn't come from the anomalous Hall current just being spin-polarized because it's in a ferromagnet, right? There are actually considerations from the electronic structure which is changing the value of this. All right, sure? Okay. Okay, so we talked about the theory of this. Have we seen this? Yes, we have, experimentally. So here we have a very thick slab of permalloy that's about 32 nanometers. And using polar MOC, we're able to look at the deflection of the magnetization as you approach the layer boundaries. And so what we have is an electric field pointing along this direction. If we really do have these types of spin Hall currents in ferromagnets, which aren't disputed from a symmetry perspective, then those spin currents should flow to the layer boundaries and exert a torque. That torque can then be measured via the deflection of the magnetization optically. And when we do so, we can extract a lower bound for the spin Hall conductivity that's about 1,000 inverse ohm inverse centimeters. Right, so this is direct evidence of a self-torque in a ferromagnet due to the spin Hall effect. Okay, but we can also look at antiferromagnets as well. And so this is part of an experimental collaboration. Right now, I'm just going to focus on the theoretical aspect of this for the sake of time. But before, it implied that you can have a type of anisotropic spin Hall effect in a collinear antiferromagnet. So in other words, depending on the orientation of the electric field and the Nail order vector, you can get 2 different values for the spin Hall effect. And one way of probing that is to put the electric field at a 45-degree angle, let's say, from the Nail order vector, in which you can get a linear combination of these 2. So these are just theoretical Kubo calculations supporting that. Okay, so these so far have been intrinsic mechanisms. So now what I'm going to do is talk about some of the extrinsic mechanisms that we've looked at in ferromagnetic layers. And this relates to the magnetic spin Hall effect that you've heard about earlier, so I'll try to tie that in with these calculations. So what we're doing here is relatively simple. So again, under an applied electric field, we're just considering the change in the occupation of carriers, right? We're leaving the eigenstate spin currents the same. And so we can calculate all of these things from density functional theory. So using the relaxation time approximation and the group velocity, we can calculate the perturbation to the occupation, and we can then calculate the eigenstate spin currents as well. So here are the results of this sort of calculation. So it's similar as we saw before. We have a ferromagnetic layer. This is a bulk calculation. We turn on an electric field. We're going to look at the spin current that's flowing perpendicularly to that electric field, and we're going to calculate all the different spin directions as we rotate the magnetization. Okay, and so here's what we find from this, right? So in black, we have the charge current that results, right? And this charge current has essentially the angular dependence of the planar Hall effect, right? So this is what we're calculating here, the planar Hall effect. So if we look at the spin current that is polarized longitudinally to the magnetization, we could call that a spin-polarized planar Hall effect, if we like, right? But just like the calculations of the spin anomalous Hall effect, the spin planar Hall effect has a magnitude that can't be defined by the polarization times the ordinary planar Hall effect. So in other words, we are getting contributions from the electronic structure that do not just make this a spin-polarized version of the charge current. Okay? But if we just look at the other spin directions, then we get spin currents that don't look like they're aligned with the longitudinal direction. So in other words, we get spin currents where the spin direction is transverse to the magnetization. Right? So these are currents that can now exert torques on the magnetic layer. So previously, this has been referred to as the magnetic spin Hall effect. One thing that I want to point out with this plot here is that the origins of the magnetic spin Hall effect as calculated in this way are essentially the same as the origins of what I'm calling the spin planar Hall effect here. Right? That does not mean that the only way to get this sort of effect is through this type of extrinsic calculation. So skew scattering, for instance, might be able to also cause what we're calling the magnetic spin Hall effect. But there is a very close relationship between the physics of the planar Hall effect and the magnetic spin Hall effect. All right, so in the last part of the talk, I'm going to talk about so-called novel spin orbit torques in ferromagnetic layers, and I'll describe exactly what I mean by that. But to spoil the story, ultimately, what makes these spin currents or these spin torques unconventional is the fact that the two ferromagnetic layers are talking to each other within a distance of a mean free path. So this is something that kind of harkens back to the days of in-plane GMR, which is really the effect that started Spintronics from a technological perspective. Okay, so this was done in collaboration with Kirill Belashchenko and Alexei Kovalov at the University of Nebraska. We have two different formalisms that we're looking at here. So the first is the non-equilibrium Green's function formalism. And so if you're familiar with this, all of this will mean something. If it's not, it will probably look like gibberish, and it really doesn't matter. The point is that these are first principles transport calculations that calculate the scattering in this active region. And then from the lesser Green's functions, we can then calculate the torque. So this is a fairly standard procedure. It's just very computationally intensive. But we're also going to look at semiclassical Boltzmann calculations, right, which actually operate in a much more simplistic regime. So in the Boltzmann calculations, we're actually going to treat each of these layers as having a spherical Fermi surface. And to make matters even more simple, we're going to treat both majority and minority carriers as having the same Fermi surface. Right? So that might seem very strange to do in a ferromagnet. In fact, these are the way the original calculations of in-plane GMR were done in these sort of landmark papers looking at the behavior of the in-plane giant magnetoresistance. Right? So how do we calculate the effects of ferromagnetism on transport when you've got a same Fermi surface for both spins? And the answer has to do with the non-equilibrium properties. So they have different relaxation times, and it's all really through non-equilibrium that you're going to capture these properties. Okay, so again, if you're familiar with all of this, hopefully this will be useful. If not, it doesn't matter. The main point is that in our Boltzmann equation, we have the effect of the electric field of spin precession around the exchange field, which means that we can capture dephasing and spin transfer torques. And then through our collision integrals, we can put whatever we like. So we can put, for instance, at least the extrinsic version of the spin Hall effect. We can capture all of these interfacial effects like interface-generated spin currents at the boundary. So we really can capture a lot of effects with this, but just with a very simplistic electronic structure. Okay, so both the Ab-initio and semiclassical calculations revealed new torques in these ferromagnetic layers. So again, what do I mean by this? So here's the system we're going to look at. It's obviously a ferromagnetic trilayer. But the thing that we're going to do here is we're going to turn off spin orbit coupling in one of the layers. All right? But that's the layer in which we're going to look for the torque. Right? And by doing that, we guarantee that whatever is generating this spin orbit torque has to come from the other ferromagnetic layer or the interface. Right? So whatever happens here via spin orbit scattering or spin orbit effects has to travel over to this layer to exert a torque. All right? So we are going to keep M2, so the magnetization of the layer we're looking at the torque without spin orbit coupling is going to be in plane, and the magnetization of the layer with spin orbit coupling is going to be out of plane. All right, so basically said all of that. Okay, so what can we take away from this? So when we rotate the magnetization in plane in the layer where spin orbit coupling is off, we're going to get two different components of torque. So one of the torques is also going to be in plane, but perpendicular to the magnetization. And we can show that that torque comes from the regular spin Hall effect in this ferromagnetic layer. So I'm not going to focus on that. It's not really interesting, new, or unconventional in any way. But we get a second torque, which is pointing out of plane. And it's not very simple to describe where that's coming from, right? So that's what I'm going to focus on. OK, so here are the results of the Ab-initio calculation. So we have cobalt, copper, cobalt. Again, we're going to rotate this magnetization in plane, but we're able to turn spin orbit coupling off here. So we know that the torque has to rise from something that's happening over here. And so here I have the two components of torque. One is this in-plane torque, which we can explain from the spin Hall effect, and this out-of-plane torque here, which has this sinusoidal type of relationship. So if you look at all of the different spin currents that can be created in this generating layer, the spin currents that would cause this sort of torque are not allowed by symmetry. So that's the puzzle. That's the paradox, right? There's nothing looking at any sort of bulk or interfacial theory here that can actually cause this type of torque. Now, there is one possibility that the spin Hall current can come here, and through an abnormally large imaginary part of the spin mixing conductance, we can get a rotation that creates this sort of torque. But we can calculate that in this region, and it's known to be small for cobalt copper. So it's not a plausible reason for why we would get such a large out-of-plane torque, right? So again, the paradox is the torque has to be caused from this layer, but nothing in this layer can cause that torque, right? So that's what we were sort of faced with here. So we looked at this with the Boltzmann simulations because we can pick that apart a little more and try to understand the physics of what's going on. So in the Boltzmann simulations, even with the incredibly simple electronic structure, we were able to confirm that we can get similar torques. The phase relationships and the magnitudes take a bit of playing around with parameter space, but at the end of the day, we can confirm the same qualitative behavior. So we do get this out-of-plane-like torque, even in very simple spin orbit torque models. So what's causing this? How does this happen? So we need one more clue before we go into what we think the mechanism is. And if we look at this out-of-plane torque versus this in-plane torque, and we look at the amplitude of the torque as we change the spacer thickness, what we find is that the in-plane torque basically doesn't change as a function of in-plane thickness, right? So this is consistent with a spin Hall effect because it's going to decay at a spin diffusion length, and we've essentially set that to 0 in our semi-classical calculations. We would expect it to be very large in the first principles calculations, right? So we get no real change here. But we get an exponential decay of this novel out-of-plane spin torque, and it's exponential as a function of about the mean free path of the spacer layer, right? So in other words, we have a torque that is only going to activate if you're within a mean free path, right? Both ferromagnetic layers of each other. All right, so here's what we came up with as what the mechanism is, right? So what we have, we can sort of describe in 3 steps, right? So the first step is we have an in-plane charge current, and that's going to create an in-plane spin-polarized current, right? It's very standard in a ferromagnetic material. We also know through all the original studies of in-plane GMR that that in-plane current leaks, right? And it decays on the order of a mean free path. So if these layers are within a mean free path of each other, this in-plane spin-polarized current, which is rotating its polarization with the magnetization, right, as we rotate the magnetization, is going to leak into this layer. Once it leaks into this layer, if we look at the conversion processes that are available at the interface, spin orbit scattering can convert this in-plane polarized spin current into a fully out-of-plane polarized spin current. So this is sort of what was missing from before, is if you just look at this as a bulk system, you don't have this sort of in-plane spin polarized current, right? So it's really being provided by the other ferromagnetic layer, right? And so through this type of conversion, you can then get this out-of-plane current, which can then exert the torque. OK, so I'll leave my conclusions up on the board, and I'm happy to answer any questions.